Hey everyone, I wanted to go ahead and talk to you all about some lipid metabolism. Um, Before spring break, we went through lipid metabolism and kind of went from I would venture to say like the macroscopic level down to the microscopic level. So we went from basically something that you could, pick up with a spoon or something like that, down to carbon skeletons. And now what we're going to do is continue kind of where we were. So if we look at this slide, this is one of the important slides from what we did before spring break. And this was basically taking a fatty acid, depicted here at the top as our fatty acyl-CoA. This is a completely saturated fatty acid, so it has no double bonds. It has a carbonyl carbon, but that's the only place that you have a double bond. Everything after that is totally saturated. So it's a fatty acid chain. And what we do is we basically take this and break it down by removing 2 carbons at a time. Those 2 carbons are in the form of acetyl-CoA. So if this was 18 carbons long, one of our molecules, our fatty acyl-CoA, would be 16 carbons long, and our acetyl-CoA is obviously 2 carbons. Now, in order to get from that starting point to the end, well, we got a couple things going on. We're going to do an oxidation reduction reaction with this acyl-CoA dehydrogenase. We're going to insert a double bond, making this trans delta 2 enoyl-CoA. Then we're going to hydrate that by using enoyl-CoA hydratase. We're going to put a hydroxide and a hydrogen, or we're going to put a hydroxide on where that double bond was. So now we have 3L-hydroxyacyl-CoA. Our enzyme 3L-hydroxyacyl-CoA dehydrogenase is going to take that and take our hydroxyl group and make it a double bonded oxygen, so a carbonyl carbon. And one of the things that I highlighted was, and wanted you all to recognize and kind of see this as, is basically what we're doing is we're taking where we previously had a single carbonyl carbon, we're adding another carbonyl carbon. We're making this little group right here that I put a box around. We're almost making it kind of symmetrical, because what we're going to be able to do is use the enzyme beta-ketoacyl thiolase, or beta-ketoacyl CoA thiolase, and put coenzyme A onto this second carbonyl carbon. And in the process, we're going to release our acetyl-CoA group. So our acetyl-CoA, this which I've put a box around, is going to be released. And then we're going to put coenzyme A and link it up to that carbon. So S-co, I need to get my tablet. Right now I'm just using one of my kids' mouse. It's singular. So that's essentially what we're going through when we talk about beta oxidation. And that's the nuts and bolts of it all. What I want you to remember, first and foremost, that highest level, or that, I don't want to call it superficial, but that level of understanding that I guess is kind of like the most shallow, would be you're removing 2 carbons at a time, and those 2 carbons are coming off in the form of acetyl-CoA. Now, thinking about that acetyl-CoA, what can you do with that? Well, that acetyl-CoA can feed into the citric acid cycle. Then our fatty acyl-CoA that's 2 carbons shorter, we're just going to send it back up the top and send it right back through, removing 2 carbons at a time. We'll repeat this over and over again until we get down to a molecule that's 4 carbons long, and we'll split that 4 carbon long molecule into 2 acetyl-CoA molecules. Now, here's another depiction of what's taking place there. So that other depiction is, well, it's essentially the exact same things, but with a slightly different model. We're using acetyl-CoA dehydrogenase, and we're putting a double bond in. So this is kind of an important point of reference. We're taking a saturated fatty acid, and we are temporarily making it an unsaturated fatty acid. So we're putting a double bond into this molecule. We're going through and we're making our acetyl-CoA, releasing that. Now, this beta oxidation is going to occur in the mitochondria. All right, so proceeding onward, let's talk about the beta oxidation of palmitic acid, a completely saturated 16-carbon long fatty acid. That will go through a total of 7 rounds of beta oxidation. Now, this number is always something that seems a little bit odd, because if you think about this as each round yields a 2-carbon long molecule, then 16 divided by 2 is 8. So wouldn't it do 8 rounds? That's a fair thing to think about, but let's think about this. The first round is going to make a 2-carbon and a 14-carbon. The second round is going to make another 2-carbon and a 12-carbon long molecule. Ultimately, what we're going to do is we're going to get down to a 4-carbon molecule. And that 4-carbon molecule is going to be split into acetyl-CoA, a 2-carbon molecule, and a 2-carbon shorter molecule, which also happens to be acetyl-CoA, which is a 2-carbon molecule. So whenever you see, a 26-carbon long fatty acid, well, naturally you'd think divide by 2, 13 rounds, but it's actually only going to go through 12 rounds of beta oxidation. Okay, now that we've cleared that up, the next thing is, what does each one of these rounds of beta oxidation do? Well, these rounds are going to produce 7 FADH2, 7 NADH, 8 acetyl-CoA molecules. These FADH2 and NADH are simply through the rounds of beta oxidation. The rounds of beta oxidation. The acetyl-CoA, by contrast, is going to be one of our products. That's going to go through the citric acid cycle. Now, these FADH2 and NADH, well, ideally they're going to produce a total of 14 and 21 ATP, but in reality it's going to be closer to 10.5 and 17.5 ATP. Now, our acetyl-CoA, those 8 acetyl-CoA molecules are going to go through the citric acid cycle, or the tricarboxylic acid cycle, the TCA cycle, the Krebs cycle, any of these things that you want to call them. And what we're going to generate from those 8 acetyl-CoA is we're going to get 8 GTP. We're going to get 24 NADH, 8 FADH2. Now those 8 GTP are equivalent to 8 ATP. The 24 NADH from the citric acid cycle, 72. The 8 FADH2 are going to be approximately 16. And then let's go on to our so-called actual numbers, 8, 60, and 72 respectively. Okay, what that means is that in actuality, it's pretty reasonable to say that a 16-carbon long fatty acid is going to produce a grand total of 108 ATP. The nominal number would be 131. So I think that it's fair to say that a 16-carbon long fatty acid is going to produce comfortably between 108 and 131 ATP. Now, the fatty acid to fatty acyl-CoA, so this is just to get the wheels turning, we have to invest a pair of ATP, and so that's going to be minus 2 ATP, so we're going to get to 129 and 106 ATP respectively. Okay, now to put things into context, that's a ton of energy. Now that volume of energy, or that amount of energy, is pretty substantial. Now, there are some hummingbirds that can traverse the Gulf of Mexico, which is more than 450 miles, during their migration from South America to Canada. They initially weigh, so that's going over the Gulf. That's completely unstopped. They initially weigh 4.7 grams. They have 2 grams of fat. That's going to give them a range of more than 600 miles, flying at 25 miles per hour. So they're going to extract a huge amount of energy from these fatty acids that they store. Now, oxidation of our fatty acids. That oxidation is going to produce a ton of energy and water. FADH2 Oxidation of that's going to give us H2O. Oxidation to NADH is also going to give us water. Effectively, 1 kilogram of fat is going to produce approximately 1.4 liters of H2O. Now, this is kind of, there's not really, we haven't really looked at anything particularly new, and I'm not going to just belabor the point of like, oh yeah, fatty acids, lots of energy, lots of energy. One thing that's important that we've previously talked about, or that we've looked at so far with respect to beta oxidation, is something that can be captured when we look at these 3 different fatty acids. Okay, what's the difference between C18.0, C18.1, C18.2? Well, C18.0 is a saturated fatty acid. C18.1 and C18.2, those are mono and polyunsaturated fatty acids. So these have 1 or 2 double bonds. Now, the question is, how is a double bond dealt with differently? Okay, so in this next figure, there's quite a lot to unpack. What I want to do is I want to focus right here at problem number 1. This is referred to as the beta-gamma double bond. What we'll notice is, let's see our carbonyl carbon. The carbon immediately after that is our alpha carbon. Just like in amino acids, whenever you think about your carbonyl carbon, the first carbon off of that is your alpha carbon. When we have a double bond between a beta and a gamma carbon in a fatty acid, we're presented with a little bit of a problem. Now, that's kind of interesting, and that's significant because if we look at this right here, where we took our saturated fatty acid and we made a mono unsaturated fatty acid, where do we put that double bond? We put it between our alpha and our beta carbons in that chain. So essentially what that means is if we had a double bond between an alpha and a beta carbon, we don't have that much of a problem. But when we have a double bond between a beta and a gamma carbon, we have a little bit of a problem. Now that problem isn't something that's insurmountable, but that's something that we just have to deal with. We have to reposition that double bond. We have to position it between our alpha and our beta carbons. So we use an enzyme known as enoyl-CoA isomerase. This is an isomerase. All that it's doing is essentially moving our double bond from between our beta and our gamma to our alpha and our beta. And when we end up with our double bond found between our alpha and our beta carbons, we have something that can basically fit back into beta oxidation. So when we have that beta gamma double bond, we want to apply enoyl-CoA isomerase. When we have that enoyl-CoA isomerase, we put the double bond in the right location, we go through beta oxidation, and if you look at this specific fatty acid, we've got actually a double bond here and another double bond here. So this enoyl-CoA isomerase is going to resolve the problem, but as we continue processing this fatty acid, this double bond right here is getting closer and closer to where we want to deal with this, or closer and closer to where we want to insert the coenzyme A and continue breaking down our fatty acid. So what we arrive at is we're able to complete 1 round of beta oxidation, and then we can begin the first oxidation of our next round. So essentially what this shows, what this right here is showing us, is what occurs when we put that double bond between our alpha and our beta our alpha and our beta carbon, but then we have a double bond between our gamma and our delta carbons. So when we look at this right here, this presents a little bit of a problem. One thing, so this 2,4-dienoyl-CoA reductase, what effectively it's going to do is take these 2 double bonds between 2 and 3 and 4 and 5 and remove them in place of a single double bond found between carbons 3 and 4. So effectively it's doing an oxidation reduction and kind of an isomerization reaction. Now what's going to result is we're going to have this molecule with a double bond between carbons 3 and 4, And what we need to do with that is now we do an isomerization. Have we seen that isomerization before? We have. We saw it with enoyl-CoA isomerase. This is, 3,2 enoyl-CoA isomerase. We're effectively taking that beta-gamma double bond and repositioning it between the alpha-beta carbons. So that can proceed through beta oxidation. Now what's also shown in this figure is that E. coli have a slightly different mechanism to deal with this. What E. coli are going to do is they're going to just remove one of these double bonds. They're going to use 2,4-dienoyl-CoA reductase and produce this 2-enoyl-CoA molecule, so with a double bond between carbons 2 and 3. So E. coli handle this sort of 2, 3, 4, 5 double bond situation differently than bacteria are going to. Okay, now arguably this is kind of a simple and straightforward fatty acid. We had to isomerize it. We have this double bond that's kind of getting closer. We're going to end up with a saturated double or a conjugated double bond situation, double bond, single bond, double bond. How do we deal with something that doesn't fall into this kind of situation or this kind of scenario? Well, when we have a molecule like 3,5,8-trienoyl-CoA, what we have is a double bond between carbons 3 and 4, 5 and 6, and between 8 and 9. Now, what that means is we've got some double bonds that are conjugated and some that are non-conjugated. Now, what we need to do with this is we need to reposition some of these double bonds. Specifically, we need to take this carbon 3,4 double bond and put it between carbons 2 and 3. By doing that, we'll make it so that we'll be able to process this fatty acid a little bit easier. Now, what we also need to do is move this double bond between carbons 5 and 6 between 4 and 5. So we're going to use the enzyme 3,5,2,4-dienoyl-CoA isomerase. That's going to move both of these double bonds. We're going to end up with something that is delta 2, delta 4, delta 8 trienoyl-CoA. Now, that will bring us back to a point where we have a conjugated double bond situation, double bond, single bond, double bond. We're going to use a reductase to remove one of those double bonds and put a single double bond between carbons 3 and 4 in place. Now, that's going to be the result of the enzyme 2,4-dienoyl-CoA reductase. We're going to isomerize that to put it between carbons 2 and 3. We can send that through beta oxidation, and we're all good and well until we get to a point where we have a double bond that is, or we've removed 2 carbons at a time, and we have a molecule where we've got something that resembles this right here. A double bond between carbons 2 and 3, and then a double bond between carbon 4 and 8. Now, just to remind you, this line right here says that basically we've removed 2 carbons. This is we've done another round of beta oxidation, removed 2 carbons. This 8 right here is not going to be 8 forever because we're cutting 2 carbons off at a time. Instead, what this is showing is that eventually this carbon number 8 will be, on a shorter fatty acid, will be carbon number 4. And we'll have a double bond between carbons 2 and 3. And then we'll have another double bond between 4 and 5, which is what we see right here. So we're going to use our dienoyl-CoA reductase. We're going to use 3,2-enoyl-CoA isomerase. And then we're going to get a molecule that we can send through beta oxidation, and we'll be good to go. So essentially, what we need to do whenever we see a double bond or a monounsaturated fatty acid or a polyunsaturated fatty acid is look at it and ask the question, well, where is that double bond? What are the implications of that double bond? Now, if you have something, like if you have a fatty acid, let's say we have a fatty acyl-CoA that looks like this. Mhm. Okay, we've got that. And let's say that my alpha carbon, let's say that I've got, let's say it looks like this. Does that present a problem? It really doesn't, because arguably that's the position that I want my fatty acid to be in. If I have a monounsaturated fatty acid with a single double bond, or obviously it's a monounsaturated fatty acid, but if my monounsaturated fatty acid has a double bond right there, arguably I'm able to skip a couple of steps of beta oxidation. Now, let's take this another direction. If I have a double bond right there, if I have a double bond right here, does that really present a problem in the immediate? It doesn't. This molecule is going to undergo a couple of rounds of beta oxidation. And eventually, that will present a problem. But for the first little bit, I'm going to be able to go through beta oxidation, process this fatty acid, pluck 2 carbons off at a time, and move on. So this is a more detailed look at our problem number 1, the gamma beta double bond. And so here we've got this double bond between carbon number 3 and carbon 4, also depicted as the delta 3 double bond. Now, what we want to do is simply move it. Move that double bond to be between carbons 2 and 3. Enoyl-CoA isomerase does that job for us. Our second problem, delta 4 double bond. What do we do with that? Our first step is just fine. However, during our delta 2,4 dienoyl acyl-CoA will not fit into the active site, our enoyl-CoA hydratase. And this right here will not fit into the active site. That's really the heart of the issue. So this is not just we can't do it because something said so. Instead, we have an enzyme that is trying to interact with these molecules. And depending on the placement of double bonds, depending on any sort of modifications to this molecule, it's either going to fit or it's not going to fit. It's going to act or it's not going to act. Now, that's where we're really running into an issue. If it doesn't work, it doesn't work. So we have to figure out a way to deal with this. And so our solution, bacteria are simply going to reduce that delta 4 bond. Mammals are going to do the same thing, but through a series of steps. And that's what we looked at with our 2,4-dienoyl-CoA reductase and that enoyl-CoA isomerase. Now our third problem is the reverse reaction of our enoyl-CoA isomerase. Excuse me. Where we have to deal with the placement of these double bonds and find something that ultimately is going to look similar to the issues that we saw with our first problems. And we need to get to a 2,3 double bond so that we can process this fatty acid properly. So we'll use parts of problem number 2, that delta 4 double bond, in the process. All right, so those are our kind of simple models for fatty acids. If you have a completely saturated fatty acid, you just go through beta oxidation. If you have a monounsaturated fatty acid, you'll ultimately care about where that fatty acid or where that double bond is. If that double bond is between carbons number 16 and 17, you don't care about it for a while, so you can kind of ignore it. But whenever it gets close to where you're putting a double bond in and doing your oxidation reduction reactions, you'll then begin to worry about it. Maybe not worry, that's dramatic, but you'll begin to think twice about it. Now, similarly, fatty acids with an odd number of carbons. Okay, let's think about some odd numbers. 3, 4, 1, 7. 19, 25, 15. These are all great odd numbers. Now, with that in mind, it's kind of like dealing with a monounsaturated fatty acid where the double bond is between carbons number 13 and 14. When you are trying to make an acetyl-CoA molecule, plucking 2 carbons off at a time, you don't care what's going on between carbons number 13 and 14. So what we're interested in for quite some time is we could care less about, a fatty acid being 17 carbons. We care about what's going on between carbons 1 through 3, basically. 1 through 4. We care about putting a double bond in, hydrating it, releasing succinyl-CoA, or not, releasing acetyl-CoA. Now, like I said a moment ago, when you get down to a molecule that's 4 carbons long, you're going to split that into 2 acetyl-CoAs. I'm going to say 2x here, just by virtue of splitting it and using coenzyme A to do as much. Now, with that in mind, so every odd chained fatty acid will ultimately become, every even numbered carbon fatty acid will ultimately get down to 4 carbons long. Similarly, every odd numbered fatty acid will eventually get down to a 3 carbon long fatty acid. That 3 carbon long fatty acid is a molecule known as propionyl-CoA. Okay, so propionyl-CoA is 3 carbons. If we were just to split this and release an acetyl-CoA, then we're dealing with a 1 carbon molecule. And that's not really something we can easily deal with. So we actually don't want to do that. Instead, what we want to do is take this from a 3 carbon molecule to a 4 carbon molecule. Because as soon as we get this to a 4 carbon molecule, then we can do something a little bit more familiar with it. Okay. Now, propionyl-CoA, the first thing that we're going to do is use an enzyme known as propionyl-CoA carboxylase. That enzyme is going to carboxylate our propionyl-CoA. So we're going to use ATP, the hydrolysis of ATP, to drive the addition of this CO2 onto propionyl-CoA to make S-methylmalonyl-CoA. So this is a 4 carbon molecule. It's not a 4 carbon chain, or it's not a 4 carbon straight chain, but it's 4 carbons nonetheless. Now from that, we're going to get, well, oh man, this is bonkers. We're going from S-methylmalonyl-CoA to R-methylmalonyl-CoA. We are isomerizing, making the other component of a racemic mixture, making this R-methylmalonyl-CoA. That is the natural substrate. That's an appropriate substrate for the enzyme methylmalonyl-CoA mutase. That methylmalonyl-CoA mutase is going to rearrange these 4 carbons to make succinyl-CoA. Okay, now what it's going to use as a cofactor is vitamin B12. I believe that's riboflavin, if I remember correctly. So it's going to use vitamin B12 to do all of this. Succinyl-CoA. Man, where have we seen that before? Oh yeah, that's right. The citric acid cycle. So we're converting an odd-numbered fatty acid to an even-numbered molecule. So we're going from 3 carbons of propionyl-CoA to 4 carbons of succinyl-CoA. I apologize for yawning. We're going to rearrange this carbon skeleton. Now this is a difficult reaction and requires vitamin B12 and some free radical chemistry. This methylmalonyl-CoA mutase, this is what's going to be responsible for doing it. We're going to take the carbon skeleton from this structure right here to this structure right here. Now, what's going to help us do this is deoxyadenylyl cobalamin. This contains cobalt. Now, one thing that I want you to recognize about this is, heck, we've got 1, 2, 3, 4 rings that come together to make one big ring. That big ring, well, it looks a lot like a heme ring. One of the biggest differences that stands out to me is that right here we've got a cobalt instead of, what do we have in heme? That's right, iron. Now, this is our vitamin B12 that's going to help us catalyze this reaction. Now, what we've got going on here is we want to move this right here to that position right there. So how are we going to do it? Well, we're going to do it with the help of vitamin B12. And what we're effectively going to do is we're going to use this adenosine from our vitamin B12 to remove this hydrogen, removing that from that carbon right there. And in the process, that's going to give us a free radical. That is known as cyclopropyloxy radical. That cyclopropyloxy radical is going to help us move that carbon and that coenzyme A to where our radical was. And then we're going to move our radical to where our S-CoA was. Now, what's going to result from that is we're going to get rid of that radical, and in the process we're going to make succinyl-CoA. Here's our 1, 2, 3, 4 carbons in a row, as opposed to 1, 2, 3 carbons in a row shown up here. We've got 4 carbons in a row. We are good to go with that succinyl-CoA. Those are just all the junctions. So a vitamin B12 deficiency, you could think about this in effect as cannot metabolize odd number FA, or fatty acids. Now, vitamin B12 can be synthesized by certain bacteria in the gut, not by plants or animals, but instead these bacteria that live in your microbiota, or your microbiome, your gut bacteria. They reside within some of the bacteria within your gut. The intrinsic factor binds B12 and allows absorption. Humans need approximately 3 micrograms per day, and they usually store a 3 to 5 year supply in the liver. So vitamin B12 is arguably pretty stable. Insufficient B12 leads to pernicious anemia. There's going to be a drop in red blood cells and hemoglobin, which leads to a drop in neurological function. So this vitamin B12 deficiency can lead to neurological disorders. This is often fatal in elderly peoples, and usually what we have is insufficient intrinsic factor. Now, succinyl-CoA, which is one of our endpoints in this, is a molecule found within the TCA cycle. You might think we have arrived at the end of the story, but not the case. Succinyl-CoA is a TCA intermediate and not a substrate. It can go round and round the TCA cycle, but no net degradation will occur. Each round of the TCA cycle, you'll lose 2 carbons, but you'll add 2 more. To get out of this loop, you need to convert succinyl-CoA to pyruvate. That pyruvate is going to lead to 3 CO2s through the citric acid cycle. Beta oxidation is the equivalent of succinate, which is right here, to oxaloacetate right there in the TCA cycle, which all occurs in the mitochondria. So essentially with beta oxidation, we're using things from here to there. Now, to convert succinyl-CoA to pyruvate, we have succinyl-CoA being converted to malate through the citric acid cycle. The malic enzyme is able to take malate NADP plus to make pyruvate NADPH and CO2. So have we used this reaction before? Well, we have. Now, we use that whenever we were talking about malate dehydrogenase. Okay, now beta oxidation in peroxisomes. Essentially, in animals, this is able to take particularly long fatty acids, so the fatty acids that are more than 22 carbons long. If you're dealing with a fatty acid that's 20 carbons long, beta oxidation all day. Beta oxidation in the mitochondria. But if it's 24 carbons long, 23 carbons long, you got to send it to the peroxisomes. Now, the first reaction is going to be a little bit different because this is not going to feed into the electron transport chain. Because peroxisomes don't have an electron transport chain. So what that means is you're going to get 2 less ATP, because if you remember that very first step in beta oxidation, it's generating some FADH2 that leads into the electron transport chain. Our first enzyme was acyl-CoA oxidase. That Fa-CoA plus O2 yields enoyl-CoA and hydrogen peroxide. All right, so ketone bodies. These are water-soluble compounds, which are a good way for the liver to send energy-rich compounds to peripheral tissues when sugar levels are low. You need oxaloacetate to oxidize acetyl-CoA through the citric acid cycle. Now, if oxaloacetate concentrations are low, acetyl-CoA is going to be metabolized in to make ketone bodies. Ketone bodies can be used for fuel by heart, muscle, and brain. And normally, the brain usually uses glucose, but ketone bodies can be used under starved conditions. And next up. So here what we have is molecule acetoacetate being spontaneously converted into acetone. We also have this molecule D-beta hydroxybutyrate being interconverted through an oxidation reduction reaction to acetoacetate. Now, ketone bodies generally have a very low concentration, but under starved conditions or when people are surviving and living on a low-carb diet, what's going to happen is that TCA cycle intermediates are going to be metabolized to make glucose to fuel the brain. Fat is going to be metabolized by being converted to acetyl-CoA, and ultimately we're going to lead to the production of the increase of ketone bodies. Now, for people who have diabetes, their cells, one of the potential issues is their cells can't take up glucose efficiently, which leads to the sensation or the cell believing that it's basically starved. Now, what this means is that ketone body concentration is going to go up, acetone concentration is going to go way up, and blood pH is going to go down. These ketone bodies are somewhat acidic. Now, all of this put together, one thing that's really important to recognize is that this is basically unmonitored or uncontrolled diabetes. What can happen? This isn't to say this is what happens, but this can happen. I'm not a physician, but if I remember correctly, I believe this is a state known as diabetic ketoacidosis, or DKA, diabetic ketoacidosis, which, if you look at the blood pH going down, acidosis, those two things kind of go hand in hand. Now, with that said, this unchecked or unmonitored diabetes can lead to this, which a decrease in blood pH, increased concentration of ketone bodies and acetone, can lead to disorientation, urination, and incontinence, ultimately lead to a coma and potentially into death. Now, in some cases, this can unfortunately be mistaken for alcohol intoxication because somebody might be slurring their words or speaking in a kind of unnatural cadence, and it has doesn't have to do with their um, blood alcohol level or anything of that nature. Instead, it's simply that they have maybe undiagnosed diabetes, and this is just what's happening. Now, with that in mind, the first step in ketone body synthesis is reverse of the last step in beta oxidation. So our last step in beta oxidation, we have this molecule right here, acetoacetyl-CoA, a 4 carbon long molecule. And that 4 carbon long molecule is split into acetyl-CoA and acetyl-CoA. So that's beta oxidation. When we're going the opposite direction, we're going to use the enzyme thiolase, also known as acetyl-CoA acyltransferase or acetyltransferase. That is the enzyme that is going to take two acetyl-CoA molecules and combine them to make acetoacetyl-CoA. Now in this figure, what we have is these two carbons depicted in black, indicating that those two carbons are them. These two carbons right here are depicted in kind of a maroonish color, and that's what we're talking about right there. Now, HMG-CoA, this enzyme, hydroxymethylglutaryl-CoA synthase, also known as HMG-CoA synthase. This enzyme is very important because it produces this molecule known as beta-hydroxy-beta-methylglutaryl-CoA, or HMG-CoA. This is a key intermediate in both ketone body and cholesterol biosynthesis. So acetoacetyl-CoA ultimately is going to be, or we're going to metabolize that by adding a total of 2 carbons onto this. So our acetoacetyl-CoA is 1, 2, 3, 4. We're going to take this molecule right here, this acetyl-CoA, and we're going to take carbon number 2 on acetyl-CoA and basically form a bond between 2 and carbon number 3, which is going to result right here. Our terminal carbon in this molecule is CO2, and we see it depicted right there. So HMG-CoA, beta-hydroxy-beta-methylglutaryl-CoA has 1, 2, 3, 4, 5, 6 carbons. Where did they all come from? They all came from the same source of acetyl-CoA. So 3 acetyl-CoA are required to make HMG-CoA, a 6-carbon long molecule. Were all these acetyl-CoAs just sort of thrown into a blender? No, we had different enzymes working in different places. HMG-CoA lyase is the first committed step in ketone body synthesis. Now with this enzyme, what we're going to do, beta-hydroxy-beta-methylglutaryl-CoA, or HMG-CoA lyase, what it's going to do is remove acetyl-CoA. Remove one of our first 2 original acetyl-CoA molecules. And we're going to end up with acetoacetate. So acetoacetate is 1, 2, 3, 4 carbons. It's got this CO2. And what was one of the things that was mentioned previously is that, yeah, that's right, that these ketone bodies are soluble. That CO2 right there, that double bonded carbon with that negatively charged oxygen, makes this fairly soluble, makes this something that can move through an aqueous environment pretty easily. So here is our summary of the steps of ketone body synthesis. 2 acetyl-CoAs come together to make acetoacetyl-CoA. A third acetyl-CoA is mixed into the fold by HMG-CoA synthase to make HMG-CoA. This molecule is super important for obviously ketone body synthesis, but also cholesterol synthesis. HMG-CoA lyase cuts off 2 of those carbons, leaving behind acetoacetate, a 4-carbon long ketone body. Now, acetoacetate can be converted to beta hydroxybutyrate or spontaneously to acetone and CO2. So this really, it should show CO2 because we're going from 1, 2, 3, 4 carbons down to 1, 2, 3, and this carbon right here, well, nothing's really happening to that. Everything's happening on this carbon right here. And the thing that's happening is that CO2 right there. What's to do with that? Well, when we're going from acetoacetate to acetone, well, it's just going to be released as CO2. That acetoacetate, this molecule right here, can also go in the direction of beta hydroxybutyrate. So again, 1, 2, 3, 4 carbons long, but rather than having that carbonyl oxygen, we have an OH and an H there. That beta hydroxybutyrate, that can undergo the conversion to acetoacetate right here with the beta hydroxybutyrate dehydrogenase, and then 3-ketoacyl-CoA transferase, where we're going to make acetoacetyl-CoA, and then ultimately split that into a pair of acetyl-CoA molecules. So this is how we can metabolize a ketone body. So beta hydroxybutyrate, 4 carbons long, doesn't, like, that's soluble. It can go into the bloodstream, go to these different tissues, but what happens when those different tissues get it? Those different tissues have a mitochondria, and they say, okay, well, I want to get something that goes into the mitochondria. And what they can do is take that and convert it to acetyl-CoA. If they can do that, then this acetyl-CoA can go on through the citric acid cycle, making NADH, FADH2, and GTP in the process. So this is a good way to get energy into other locations.